My name is Yusuke Manita. I'm a PhD student of Kyoto University. Today, I'm going to talk about distinguishing ultralight dark matter spin with gravitational wave detectors. This talk is based on the ongoing work with Hiroki Takeda, Kazuki Aoki, Tomohiro Fujita, and Shinji Mukoyama. The main concept of our research is the dark matter search with gravitational wave detectors. The gravitational wave detectors are the devices that capture small variation in arm length with high precision. Of course, such variations are usually caused by the gravitational waves, but in principle, gravitational wave detectors can capture anything that changes their arm length. One of the dark matter model called ultralight dark matter can interact with the gravitational wave detectors and change the arm length. So it may leave a detectable signal in the gravitational wave detectors. Let me show the basic nature of the ultralight dark matter. Ultralight dark matter is a dark matter model with a really tiny mass in the range of 10 to minus 22 to 1 electron volt. The typical mass of WIMP is like giga electron volt. So the ultralight dark matter has literally light mass. I will show you 4 features of the ultralight dark matter. First, the ultralight dark matter must be a bosonic particle because fermionic particles are not possible to be dense enough like inside the dark matter halo due to the Pauli blocking. So the spin of the ultralight dark matter must be an integer like 0, 1, and 2. Secondary, the ultralight dark matter has a typical length scale called Compton wavelength. The Compton wavelength is larger because the mass is tiny. Thus, it can be regarded as a classical wave which oscillates at Compton wavelength. Thirdly, the ultralight dark matter is a non-relativistic wave because the local speed of dark matter is about 10 to minus 3 in the unit of speed of light. Fourth, the ultralight dark matter has a long coherent time. For example, in the case of the mass is about 10 to minus 12 electron volt, the coherent time scale is about 7,700 seconds. So, in the gravitational wave detectors, the ultralight dark matter signal looks almost monochromatic wave with the Compton wavelength, and it is almost coherent signal within the coherent timescale. More precisely, the ultralight dark matter within the mass range of 10 to minus 14 to 10 to minus 11 electron volt can be detectable in the gravitational wave detectors. The typical frequency of the signal is given by Compton wavelengths. Thus, the dark matter mass with 10 to minus 12 electron volt corresponds to 242 Hertz. It's in a Light band. So it may be possible to leave the signal in the ground-based detector like LIGO. So all the ultralight dark matter within this mass range is expected to leave a signal. But technically speaking, the way to leave the signal are different for each spin. The spin zero ultralight dark matter, such as QCD action and action-like particle, leaves a signal by fluctuate the fundamental constant like a fine structure constant and the fermion masses. The spin 1 ultralight dark matter, such as dark photon, leaves a signal by pushing the mirror of the gravitational wave detectors through the new Coulomb force. And the spin to dark matter is originating from the gravity sector, so it's universally coupled to all the matter fields, like the usual gravitational field. Thus, it leaves a signal in the gravitational wave detectors in the same way as the usual gravitational wave. So can we distinguish the spin of ultralight dark matter from the signal in the gravitational wave detectors? In fact, it seems challenging to distinguish between spin 1 and spin 2 ultralight dark matter by only using the power spectrum at the high frequency range. At the low frequency region, like lower than 30 Hertz, spin 0, spin 1, and the spin 2 ultralight dark matter give a different power spectrum. This plot shows the normalized power spectrum around 10 Hertz. The red curve represents spin 0, blue curve represents spin 1, black curve represents spin 2 ultralight dark matter signal. So they are different. So there is a possibility to distinguish. On the other hand, at high frequency region, like larger than 30 Hertz, while spin 0 and spin 1 ultralight dark matter give different power spectrum like this, the power spectrum of spin 1 and spin 2 ultralight dark matter are completely same. So it seems challenging to distinguish between spin 1 and spin 2 ultralight dark matter only with the power spectrum. So this is our question. How can we distinguish spin 1 and spin 2 ultralight dark matter signal at the frequency range larger than 30 Hertz? The brief answer is that they can be distinguished by using cross-correlational analysis with multiple gravitational wave detectors. Currently, there are 5 or more ground-based detectors in existence. Thus, 10 or more combinations of cross-correlation can be considered. The cross-correlational signal is defined like this. The small s represents the output of the detectors, and the A and the B represent the different detectors. With the cross-correlational signal, we can also define the signal-to-noise ratio of cross-correlation. And the signal-to-noise ratio is expressed like this, and the overlap reaction function, gamma is a quantity that represents the dependency of the signal-to-noise ratio on the relative position and the direction of 2 detectors. And the overlap reaction function for spin 1 and spin 2 ultralight dark matter have different dependencies on the detector's position and angle, like this. In this expression, beta represents the angle between two detectors, like this, and delta represents the relative orientation of these detectors. This difference of overlap reaction function in spin 1 ultralight dark matter and this spin 2 ultralight dark matter is originating from the finite time light traveling effect in spin 1 ultralight dark matter signal. In the usual gravitational waves and spin 2 dark matter signal, the finite time light traveling effect is negligibly small, but due to the vector nature of in spin 1 ultralight dark matter, the usual conventional effect is suppressed, and the finite time light traveling effect can be dominate. So anyway, thanks to the difference in overlap reaction function, like this, the cross-correlational analysis can identify the signal as spin 1 or spin 2. Let's consider the spin distinguishability with overlap reaction function. We define the indicator of the distinguishability as the difference between the signal-to-noise ratio of spin 1 and spin 2 ultralight dark matter signal. As a case study, we suppose that a signal is detected through the cross-correlational analysis between LIGO Livingstone and LIGO Hanford. Then we got this plot. This plot is representing the distinguishability normalized by the observed SNR by Livingstone and Hanford. At the low frequency region, about lower than 30 Hertz, since the effective overlap reaction function for spin 1 and spin 2 ultralight dark matter is the same, the distinguishability is relatively low. And on the other hand, at the high frequency region, about higher than 30 Hertz, since the finite time light traveling effect dominates, the distinguishability of spin is relatively high. The reason why it has a divergence here is that the signal-to-noise ratio of the Livingstone and Hanford becomes 0 because the finite time light traveling effect and the conventional effect is balancing at this point. As a byproduct, we found that the current constraint of the coupling constant for spin 1 ultralight dark matter, precisely speaking, U1B-L gauge boson, is reduced by about 2 orders of magnitude. The LVK collaboration has already published the upper limit of the coupling constant of the U1 ultralight dark matter. They have applied the usual overlap reaction function like this. This is the same as the usual gravitational waves, but it is modified like this due to the finite time light traveling effect of the spin 1 ultralight dark matter. Thus, we estimate how the constraint is changed. This figure is adapted from the collaboration's paper, and the red region represents the upper bound of the coupling constant by cross-correlational analysis, we added these green lines, and lower the dashed green line moved to the solid green line. It changes about 2 orders of magnitude. This is a summary. We have considered a method to distinguish the spin of the ultralight dark matter signal in the gravitational wave detectors, especially spin 1 and spin 2. We found that multiple detectors may be able to distinguish spin 1 from spin 2 by difference in overlap reaction function at f larger than 30 Hz. In my opinion, by combining the analysis of the power spectrum, we can completely distinguish the spin of ultralight dark matter because the power spectrum of the spin 1 and spin 2 ultralight dark matter signal is different in this region. And we also found that the constraint of the spin 1 ultralight dark matter by the LVK collaboration should be relaxed. That's all. Thank you for listening.